This is Number Theory, Lecture 20. And today, I'm going to talk about primitive roots. So let's just recall, we have m, a positive integer, and a, an integer, which is relatively prime to m. So what is called the order of a modulo m is the smallest positive integer d such that a to the d is congruent to 1 mod m. And we know there is such an integer because we recall Euler's theorem that a to the phi of m, the Euler phi function, is always congruent to 1 mod m. So this integer d, phi of m is a positive integer, and the smallest integer will certainly be no bigger than phi of m. Moreover, d divides phi of m. And we saw this previously, but I'll show it again. By the division algorithm, we can write phi of m divided by d. You get d times q plus r, where r is between 0 and d minus 1. So if we look at congruences modulo m, a to the phi of m is congruent to 1 mod m, but phi of m is dq plus r, which is the same as a to the d q times a to the r. Right? I'm just saying that a to the dq plus r is a to the dq times a to the r. That's just the usual rule for exponents. And a to the dq is a to the d to the q. But a to the d is congruent to 1 mod m. So this is 1 to the q or 1. This is congruent to a to the r mod m. But r is strictly less than d minus 1. And d is the smallest exponent, such that a to that exponent is 1 mod m. So it must be that r is equal to 0. If r were positive, that would contradict d being the least positive integer with this property. And if r is 0, phi of m is d times q. That is, that's a proof that d divides phi of m. And it's interesting to compute the least non-negative residues of the powers of a number modulo the powers of a mod m, and look for the first time you get 1. So suppose we take m to be 7 and a to be 2. So 2 to the first power is congruent to 2 mod 7. 2 squared is 4. 2 squared is congruent to 4 mod 7. 2 cubed is 8, but 8 is congruent to 1 mod 7. So the first power, the smallest power of 2 congruent to 1 mod 7 is 3. So this says that the order, this is our notation, the order of 2 mod 7 is equal to 3. Right. Any questions about that? This compute the order of 3 mod 7. So we have to take powers of 3. 3 to the first power is congruent to 3 mod 7. 3 squared is 9, is 2 mod 7. 3 cubed, we can do it in several ways. 3 cubed is 27. 27 is 6 mod 7. 3 to the fourth is 81. Divide 81 by 7, you get 4. 3 to the fifth is 243. Divide 243 by 7. You get 5. 3 to the sixth, 729. Divide that by 7, you get 1. So the first power of 3 congruent to 1 mod 7 is the sixth power. So the order of 3 mod 7 is equal to 6. And notice several things. Phi of 7 is equal to 6. So we know that 3 to the sixth has to be 1 mod 7, but does not necessarily, it's not necessarily true that 6 is the smallest power, but in this case it is. And moreover, every A relatively prime to M is of the form 3 to the K congruent to A mod 7 for some K between 1 and 6, right? You have 1, 2, 3, 4, 5, 6. So every congruence class is a power of A mod 7. And we say that an integer A is a primitive root mod P if two equivalent things happen. Either the order of A mod is a primitive root of A mod M, not just a prime. It's the order of A mod M is phi of M, or equivalently, if every A relatively prime, or every number B relatively prime to M is of the form or satisfies the congruence B congruent to A to the K mod M
Got them.
for some K. Okay. Another way of saying this is, if you look at the congruence class is mod M, and in that ring, this is the set of congruence classes A plus MZ, where A and M are relatively prime. So this is a multiplicative group. You multiply any two elements that are relatively prime to M, and you get another element that's relatively prime to M. This is a cyclic group generated by a primitive root. If a primitive root exists. So, for example, if you look at the ring of integers mod 7, The multiplicative group is all the congruence classes A plus 7Z, A equal 1, 2, 3, 4, 5, or 6, or 0, same thing. Sorry, 1, 2, 3, 4, 5, 6, not the same thing. This is the set of all powers 3 to the k plus 7z. K goes from 0, 1, 2, up to 5. Okay. So every congruence class relatively prime to 7 is a power of 3 mod 7. Okay. So 3 is a primitive root mod 7. 2 is not a primitive root mod 7 because 2 cubed is congruent to 1 mod 7. Let's consider the case m equal 8. What are the congruence classes, or what are the integers relatively prime to 8? It's the odd numbers. 1, 3, 5, 7. What are the orders of these elements mod 8? Well, 1 to the first power is 1 mod 8. So the order of 1 mod 8 is 1. 3 squared is 9, is congruent to 1 mod 8. So the order of 3 mod 8 is 2. 5 squared is 25, is congruent to 1 mod 8. So the order of 5 mod 8 is 2. And 7 squared is 49, is congruent to 1 mod 8. So the order of 7 mod 8 is 2. So there does not exist, there is no integer a such that the order of a with respect to the modulus 8 is equal to phi of 8, which is 4, right? There are 4 congruence classes relatively prime to 8. So there is no primitive root mod 8. So there's not a primitive root with respect to every modulus. So there is for 7, there's not for 8. Let's just, for fun, look at another example. Suppose I take the modulus to be 10. So what is phi of 10? So the numbers that are relatively prime to 10, between 1 and 10, are 1, 3, 7, and 9. Z mod 10Z star, this consists of the congruence classes 1 plus 10Z, three plus 10Z, 7 plus 10Z, and 9 plus 10Z. There are 4 numbers between 1 and 10 that are relatively prime to 10. Let's compute their orders. So 1 to the first power is 1 mod 10, of course. So the order of 1 mod 10 is equal to 1. Let's see. 3 to the first power is 3. 3 squared is 9. 3 cubed is 27, which is congruent to 10. This is congruent to, congruent to 7. This is all mod 10. 3 to the 4th power is 81, is congruent to 1 mod 10. So this says that 3, the order of 3 mod 10 is equal to 4. That's the highest, it's the smallest power of 3, congruent to 1 mod 10, which is phi of 10. So 3 is a primitive root. Let's compute the orders of 7 and 9, because it's always kind of fun. 7 to the 1st power is congruent to 7 mod 10. 7 squared is 49. It's congruent to 9 mod 10. 7 cubed is congruent to 7 squared times 7, which is 9 times 7, which is 63. It's congruent to 3 mod 10. 7 to the 4th power is 7 cubed times 7. That's 7 cubed is 3 times 7 is 21. It's congruent to 1 mod 10. So the smallest power of 7, congruent to 1 mod 10, is also 4. So the order of 7 mod 10 is also 4. So 7 and 3 are primitive roots. Mod 10. Let's see, what's the last class to consider? 9. So 9 to the 1st power, congruent to 1 mod 10. It's congruent to 9 mod 10. 9 squared is congruent to, is 81, is congruent to 1 mod 10. So the order of 9, which is back to the modulus 10, is 2. So 9 is not a primitive root. So there are 2 distinct primitive roots, mod 10, 3 and 7. So it's a useful exercise right now. Let's take our modulus to be equal to 11. It's supposed to be take A to be 2. So 2 and 11 are relatively prime. So compute, or let's just say, find the order. Well, compute is a good word. Compute the order of 2 mod 11. So what that means is you want to compute what a 2 to the k is congruent to mod 11 for k. Just start with 1 and keep going until you get a 1 over here. You want to find the smallest k such that 2 to the k is congruent to 1 mod 11. Phi of 11 is equal to 10, so 2 to the 10 is certainly congruent to 1 mod 11, but maybe a smaller power is. So I'm going to pause the recording for a minute and give you a chance to do this calculation. You want to start to compute what is 2 to the 1 congruent to mod 11, 2 squared, 2 cubed, and so forth. So spend a moment and compute these least non-negative residues. Is there an answer? Let's see. Well, there are 2 ways to do it. One is brute force. Compute every power of 2 until you get 1. 2 to the first power is 2, 2 squared is 4, 2 cubed is 8. None of them is a 1. 2 to the fourth is 16, which is 5 mod 11. 2 to the fifth is 32, which is 10 mod 11. And you could keep on going. But you can also make the following observation. Recall that we proved the order of A mod M always divides phi of M. So in case M equals 11, that's the case we're in, phi of 11 is 10. What are the divisors of 10? 1, 2, 5, and 10. So the order of any number mod 11 is 1, 2, 5, or 10. Now, if I take the number 2, 2 to the first power is not 1. 2 squared is not 1. 2 to the fifth is not 1. The only possibility left is, wow, we're done. The order of 2 mod 11, if it's not 1, 2, or 5, it has to be 10. So 2 is a primitive root mod 11. So we've seen some numbers, 7, 10, and 11, seven, 10, and 11 have moduli, have primitive roots. But when we looked at 8, there was no primitive root. So it's not true that for every modulus, there's a primitive root. And the most important case when a modulus does have a primitive root is when the modulus is a prime number. So a goal is to prove the following theorem. We're not going to prove it today, but we'll start to work on it today. All right. Every prime number P has a primitive root. And we've already seen examples of this. So if we make a little table, P and a primitive root mod P, it can be more than 1. Let's see, for what are the first primes? 2, 3, 5, 7, 11. 1 is a primitive root mod 2 because phi of 2 is 1 and 1 to the first power is 1. For the prime 3, 2 is a primitive root. Phi of 3 is 2 and 2 squared is congruent to 1 mod 3. For 5, what's a primitive root mod 5? 2 squared is congruent to 4 mod 5. 2 cubed is 8, is congruent to 3 mod 5. 2 to the fourth is 16, is congruent to 1 mod 5. So the order of 2 modulo 5 is 4. So 2 is a primitive root mod 5. Mod 7, 3 is a primitive root. And did we calculate mod 11? I thought we did. Let me see. Oh, here. mod 11. 2 is also a primitive root mod 11. 2 is not a primitive root mod 7, but it was for 3, 5, 7, and 11. But this is just an instance of the result that for every prime number p, there exists a primitive root. Right? And the proof uses some facts about polynomials. So polynomials are like integers in some ways. And what is a polynomial? So suppose R is a commutative ring or a field, a commutative ring with the multiplicative identity 1. This could be the integers, the rational numbers, the real numbers, the complex numbers. And a polynomial, say R square brackets X, is the set of all polynomials whose coefficients are in the ring R. So a polynomial is a function, if you like. It's an expression, f of x equals am x to the m plus am minus 1 x to the m minus 1 plus a1x plus a0 with all the coefficients a0, a1 up to am, elements of the ring. So polynomials you know and love, right? F of x equal x squared plus 2x minus 9 is a polynomial with coefficients that are integers, for example. Right? So these are just your ordinary polynomials. These were the simplest functions you ever saw in calculus. And we want to define the degree of the polynomial. It's slightly, you have to be a little bit more careful than you might think. Suppose you have the polynomial f of x equal x squared plus 2x minus 9. We want to say this has degree 2. Suppose you had a different polynomial. Say g of x equal to 0 times x cubed plus x squared plus 2x minus 9. X cubed is multiplied by 0. It's like it's not there. So even though you see an x cubed in this representation, this also has degree 2. So if you want to be very, and we need to be always precise, that f of x equal am x to the m, am minus 1 x to the m minus 1 plus a2x plus a1x plus a naught. This is a polynomial. And we say f of x is non-zero if at least one of the coefficients is different from 0. If ai is different from 0 for some I, and so we know that one of these, maybe all, but at least one of the coefficients is non-zero, the degree of a non-zero polynomial, the polynomial is 0, it doesn't have a degree, it's not defined. The degree of a non-zero polynomial is the largest integer d, such that the dth coefficient a sub d is different from 0. I mean, it's exactly what you know it is. It hasn't, it's not really changing, we're just being a little bit careful. And one kind of polynomial is particularly interesting. So f of x is a monic polynomial if we write it in this form, a sub m is equal to 1. That is the coefficient. So f of x equal x squared plus 3x plus 9 is monic. F of x equals 7x squared plus 3x plus 9 is not monic. That's all. Because this coefficient is 1 and this is different. They both have degree 2. And we add polynomials just the way, and multiply polynomials just the way you did in pre-calculus and calculus, right? If you have f of x is 7x squared plus 3x plus 9, and g of x is 2x cubed minus 5x squared minus 17, then f of x plus g of x, you just add them. You get 2x cubed plus 2x squared plus 3x minus 8. Right? You just adding polynomials. I mean, if in general, if you want to write it down as kind of a rule, if f of x is summation ak x to the k goes from 0 up to m, and g of x is summation k goes from 0 up to m, you can always make it the same m, because even if they have different degrees, you can add terms with 0 lead coefficients. bk x to the k. When you add them, you just add term by term. You get summation k goes from 0 to m, ak plus bk x to the k. That's your and you multiply them just the way you were taught to multiply polynomials. F of x times g of x. This is going to be some polynomial ck. Let's say they have, this goes up to m. Let's say this goes up to n. So it's sort of, if this has degree m, so degree of f equals m, and this has degree n, degree of g equals n, then the degree of f times g will be m plus n, and this will be this is ck x to the k. K goes from 0 up to m plus n, and when you multiply polynomials, you get this kind of what's called convolution. It goes from 0 up to k, a sub I, b sub k minus I. If you think about how you multiply polynomials, that's exactly the rule. So for example, if f of x is, let's see, what was the example I just had? Doesn't really matter. F of x is 2x cubed plus x plus 5, and g of x is 4x squared plus 2x minus 7, and you want to multiply them. This has degree 3, this has degree 2. So f of x, g of x, when you multiply it, you'll get x to the 5th. That's the highest power you're going to get when you multiply this times this. 2 times 4 is 8. You're going to get a coefficient of x to the 4th. When do you get an x to the 4th? I have 2x cubed times 2x. That's 4x to the 4th. That's the only time. When do you get an x cubed? I have 4x squared times x. That's 4x cubed. Minus 2x cubed times minus 7. That's 4x cubed minus 7x cubed. Sorry, minus 14. 4 minus 14 is minus 10x cubed. When do I get x squared? I get 20x squared plus 2x squared plus 22x squared. When do I get an x? I get 10x minus 7x, and my constant term is minus 35. So this is just multiplying polynomials. It's something you learned how to do by hand a long time ago, of course. And if you look at the degrees of polynomials, when you add them and multiply them, there are two simple rules. So if f of g are non-zero polynomials, the degree of f times g is the degree of f plus the degree of g. And the degree of f plus g is at most, if they have the same degree, there might be some cancellation. If they have different degrees, it's the larger. So it's at most the maximum of the degree of f and the degree of g. And the basic result about polynomials, it's easy to add, subtract, multiply, and multiply them. But just as for integers, there is a division algorithm. There is a division algorithm for polynomials. So for integers, if you take an integer a and divide it by b, you get a quotient q and a remainder which is less than the number you're dividing by. If you take a polynomial, if you take polynomials f and d is not zero, then you can write f as d times some polynomial plus a remainder, where the degree of the remainder is less than the degree of what you're dividing by. So for polynomials in with coefficients in a field, this isn't true for polynomials with integer coefficients, but if you're looking at rational coefficients or real numbers or complex numbers, for example, this is true. So f is a field, and polynomials, f of x, d of x, are polynomials in this field, and d of x is not zero. So the algorithm says there exist unique, so this is existence and uniqueness, there exist unique polynomials, q of x and r of x, such that f of x, you divide it by d of x, you get a quotient q of x and a remainder r of x. And either r of x is zero, or the degree of the polynomial r is strictly smaller than the degree of the polynomial you're dividing by d. Let's look at an example. I'll just make up examples. Suppose I have f of x equals 2x to the fifth plus 3x to the fourth minus x cubed plus x plus 1. And d of x is x squared plus 3x minus 2. So there exist polynomials q of x and d of x such that f of x is d of x q of x and the remainder r of x, and the degree of r is less than the degree of d, which is 2, which means the degree, so, and either r equals 0 or, because the 0 polynomial r of x has no degree, but if the remainder is not 0, then the degree is less than 2, which means the degree of r is 1 or 2, right? Sorry, is 0 or 1. By the way, what is a polynomial of degree 1? The degree of r of x equals 1 if r of x is of the form a1x plus a2. Sorry, the degree of r of x is 0 if r of x is a non-zero constant. This is a0 or a0x to the 0. It's a non-zero constant. So the polynomials of degree 0 are the non-zero constants. The polynomial, which is the 0 constant, has no degree. It's undefined. So how can we compute this? Well, let's do what you might have done in pre-calculus or high school or somewhere. X squared plus 3x minus 2 divided into 2x to the fifth plus 3x to the fourth minus x cubed plus x plus 1. So x squared into 2x to the fifth goes 2x cubed. This is 2x to the fifth plus 6x to the fourth minus 4x cubed. When I subtract, this cancels, I get minus 3x to the fourth plus 3x cubed plus x plus 1. X squared goes into this, minus 3x squared times. I get minus 3x to the fourth minus 9x cubed plus 6x squared. When I subtract, I get 12x cubed minus 6x squared plus x plus 1. X squared goes into this, 12x times. I get 12x cubed plus 36x squared minus 24x. When I subtract, I get minus 9x squared plus 25x plus 1. X squared goes into this minus 9 times. I get minus 9x squared minus 27x plus 18. I subtract, I get 52x minus 17. So this is my quotient, q of x, and this is my remainder, r of x. This is just, hopefully, high school algebra, certainly pre-calculus, dividing one polynomial into another. Any questions about that? Okay. I'm going to put off to Wednesday, I think, proving the division algorithm. I just want to draw some consequences of it right now. So consequences of the division algorithm. So suppose we have a polynomial f of x. You say that alpha is a zero or a root of f of x if, when you evaluate f at alpha, you get zero, right? So if f of x equals x squared minus 5x plus 6, f of 2 is 0. So 2 is a root or 0 of f of x. F of 3 is also 0. So 3 is a 0 of f of x. If we let n0 of f be the number of distinct zeros of the polynomial f of x, for this polynomial, there are at least 2 zeros. In fact, there are exactly 2 zeros, and 0 of f is equal to 2. 2 is the degree. And we have, in fact, the following theorem that f of x be a polynomial with coefficients in the field f of x not equal to 0, then the number of zeros of f is at most the degree of f of x. The degree of f. In fact, here I showed there are 2 zeros. I said there aren't any more, but you can see there aren't any more because, in fact, this polynomial factors. For this polynomial, f of x is x minus 2 times x minus 3. So f of a is a minus 2, a minus 3. Is different from 0 if a is not 2 or 3. So these are the only zeros. So that's just a quick observation. So how do we prove this inequality? Suppose we take a number alpha, divide f of x by x minus alpha. We get f of x is x minus alpha times some quotient q of x plus the remainder, where r of x is 0, or it has smaller degree than x minus 1. This has degree 1. So the only number, non-negative integer less than 1 is 0. So either r of x is 0 or the degree of r is 0, which means that r is a constant. 0 or non-zero, r of x is some constant. And what is that constant? you compute f of alpha. This is 0, alpha minus alpha, q of alpha plus r of alpha. That's r of alpha. So in fact, f of x for any alpha is x minus alpha, q of x, plus f of alpha. So if alpha is a 0 of f of x, that means x minus alpha divides f of x with no remainder. So then you can write f of x is x minus alpha times some q of x. The degree of q of x, the degree of q is the degree of f minus 1. What's the 1 plus this equals the degree of f. If f of beta is 0 and beta is not equal to alpha, then f of beta is beta minus alpha, q of beta is 0, but beta different from alpha means that q of beta is 0. So beta is a root of q. So q of x is x minus beta times, call it q1 of x. So f of x is x minus alpha, q of x, x minus beta, q1 of x. And if we proceed step by step, if alpha 1, alpha 2, up to alpha k are the distinct zeros of f of x, then f of x is going to be equal to x minus alpha 1, x minus alpha 2, x minus alpha k times some quotient q of x. And k, what is the degree of all this? K plus the degree of q equals the degree of f. This is non-negative, so k is equal to or less than that. So n0 of f, the total number of zeros of f, is at most the degree of f. Okay. All right. So what I've been talking about today is in chapter 3 of the textbook. And chapter 3 has not been uploaded to Blackboard because I don't have a PDF copy of it. I will try to get one and upload it. So if you don't have the book, then chapter 3 will be available by Wednesday, let's say, on Blackboard. But I just have to somehow come to find a PDF of it. And
So this one is part of chapter 3, this
yes,
topic?
This is chapter 3, section 1,
Okay.
polynomials and primitive roots. And we only have a half a dozen lectures left in the course, but we'll be doing chapter 3, so I need to upload a copy, and I will. You'll notice that I already. The college has a final exam schedule. The final exam is posted on Blackboard. Exactly what day and time it is. It's 8:30 to 10:30, I believe, on Wednesday of exam week, and we can't change that. That's the college schedule. For today, though, I have to
8:30?
Yes, final exams for 9 o'clock classes are always 8:30 to 10:30 at Lehman. I mean, it's been that way forever. So that's just what it is, and we all have to get up early enough to get to campus on time. But 8:30 to 10:30 is when the college schedules the final exam. It's not 9 to 11, it is 8:30 to 10:30. All right, I actually have COVID at the moment, so I'm sort of worn out even lecturing just an hour, so I'm going to have to stop for today. But we'll be back Wednesday morning at 9 o'clock. Okay. All right. That's it for today then. Thank you all. Bye.